I will do what I promised. So I will show that I will give the idea construction of order in the group. The orbit is dense. And again, this is the theorem by Machiavelli, in a very different language. And the idea that I will explain is more or less the idea of Machiavelli. Understand that the proof is in the one of the papers by Rivas. Okay, so the idea is very simple. Take a sequence of orders dense in the space of orders. And now for every order, take with respect to the canonical generator of the free group, let Bm be the ball of radius M. Now you can consider the restriction of this order to the product of the ball of radius M. Have countably many orders with finite subsets. Now the point is the following. So for each n, you have an order, then you have a dynamical realization, and you can look at the information of this order just by looking at a finite window on the real line. So for every n and m, this restriction is totally encoded by the action of the dynamical realization on some interval. So there is some interval that depends only on m and n that encodes all this information. Okay, which means that if I take the graph of the generators and I look at them at this interval, then I will re-obtain this restriction. And now what I do is to take one of these, to take all these intervals and I put them jointly on the real line. Okay, so I will get copy of it. So I translate them. Since I have a countably many intervals, I can release. And then here I had, for this order, I had the generators say F1 and F2. There was some action of them, and I will copy the actions, okay, on these intervals. And I will somehow interpolate so that they become at the end homeomorphism of the interval. So I will create some F1, capital F1 and capital F2 homeomorphism of the interval of the real line, right? Such that restricted to this translated copies of M and N, here I had this interval and then translate them. They coincide with F1 and F2 restricted to this. And this action comes from the order in this order. So I get two homeomorphisms, and in general, they will generate a free group. Okay, and now I go back in the construction. I get an order. So from this action, I get an order. Well, this order has a dense orbit. Why is that? Because I can move from one window to another one. So there is something to be done here because I move just by translation, but actually this can be done by translation inside the group. Okay, and moving the window is exactly the same as conjugating the order. Okay, and so by conjugating the order that I get here, I realize all possible informations on finite subsets of this dense sequence of orders. So I realize all possible information contained on any order on the. And this is the construction. So this is existential. So I cannot put my hands on the order, but it exists. There are some details to be filled here, but this is essentially the idea. I mean, this is very nice. This is a remark by Adam. So if I start with an order, I can connect the order with the opposite order, which means that the opposite order is the order where the positive column becomes a negative column, vice versa. And well, this is very natural because I have the action here of F1 and F2, Also, I have the action of the inverses. I put the action of the inverses in another integral, and I connect them. Okay. This is totally doable. But this only works, of course, this only works for the free group because there is no relation, no algebraic relationship. Okay, so this is essentially the graph. This is something very, very big. Okay, so in the paper of McCleary, this is somehow what is done in a very combinatorial way. And this is why this sometimes is only difficult to look at action by homeomorphism of the real line, because you avoid combinatorics and you go into discussion about infinity and things like that. Okay, so this was a question at the end of my so what about by orders? So the point here is that if you start with a by order, of course you get an action because it is a left order. So you get an action on the real line. But in general, actions on the real line do not give by orders. They only give left orders. There is no something which is invariant. And actually, when you have a by order, the action that you get is very particular. Why is that? Because the action was more or less like this. So I take, remember, there was this function gamma into the line. It was only order preserving, and the action of an element f on phi of g is equal to phi of g. Okay, so the equation is the following. So let me f of phi of g equals to phi of f of g. Remember that f was positive if and only if phi of f was larger than phi of the identity, and which is equivalent to f of phi of the identity is larger than phi of the identity. So remember that I prefer to mark this point as the origin. So f of the of 0 is positive or negative, determines whether f is positive or negative in the group. Okay, but this equation here, if the order is bi-invariant, shows the following. So if f is larger than the identity, then F G inverse has to be larger than the identity. If you wish, no, it's better. So FG is larger than G on the right. So phi of F of G larger than phi of G. And this is, because of this relation, this is F. Okay. So if I have a positive element for a by order, then it moves every point in the image of 5 to the right. So the graph of every element is like this. Like this is the diagonal. And if I have a positive element for the realization of a left orders, this is the origin. The image of 0 is a positive number, but for a by order, all the points of this form move to the right. So the graph cannot cross the diagonal. It can touch the diagonal because there might be points in the real line which are only limits of points of this way, but not point of this way. It can touch the diagonal. It can, no, this is not a homeomorphism, but it doesn't cross the diagonal. So things that cannot happen for a by order is something like this. Cannot happen for the realization. Okay. So the graph of the elements are on one side of the diagonal, okay, which is something very, very, very strange. I mean, the fact that for instance, you take any bi-orderable group. Take, for instance, the group of a fine transformation of the real line. Take the bounds like solitary. Yes, one. This embeds into the group of a fine transformation of the line. But actually, Well, the natural action is the fine action. But actually, this group is bi-orderable because there is only one bi-order for which A and B are positive. Okay. If you impose this condition, A and B are positive, and moreover, you impose the condition that the order is bi-invariant, then you get a bi-order. And then you perform this construction for this bi-order. Well, the action you get is very different from an affine action. Because in an affine action, elements cross the diagonal, and here you get something different. You can do exactly the same for the case of Thomson's group, for instance. Bi-orderable has a very complicated action on the real line, on the interval, if you wish. You get, but if you look at the action that you get from the bi-order, you get a totally different. And of course, the argument that I gave to show that the space of left orders is a Cantor set doesn't work for the case of bi-orders, because you take a bi-order, you get an action, and if you perturb the action, you will kill this property. So if you induce an order on the group, you will get something that it is not necessarily invariant by conjugacy. You will escape from bi-orders. Okay. And, so you really need to do something else. So I forgot the name, but actually, I got it. It is a very recent paper. I think it's a very recent result. This is posted on archive right recently. So the theorem by and Williami, that actually the space of bi-orders, the free group, second percent. This is really very, very big. Okay, now I want to go into the let's we have an action real line that for any element has no hyperbolic points. It's going to a bi-order. What do you mean it doesn't cross the diagonal? No, because no. I don't answer really well the question, because what about this? You have an action, an element like this, then it is the diagonal, and then it crosses. No, you don't want this. All elements are always on the same side of the. They are always on the same side of the diagonal. Yes. And you take any sequence on the real line and you get an order for this. What you get is a bi-order. Okay.
So actually, it's if and only this.
It's only if and only. Yes. So now I want to go to focus on the Conrad property. So what is the dynamical counterpart of the Conrad property? So like this, I mean, I take an order with the Conrad property and I do the dynamical realization. What special property should satisfy this dynamical realization? And vice versa. If I have an action on the real line and I induce from this action an order, what is the condition for the action in order to get something? This is so I will try to explain this without proving it. So because the proof is somehow again combinatorial, but I will try to explain why sometimes it is better to you can describe this, but somehow you have to really go into remember, one of the definitions of the Conrad's property was this fact that there is a Conrad's jump for every element and there is order on the closure, so the kind of filtration of the group, and there are many courses which are Archimedean, so there are many levels of the actions and so on. This can be done, but actually, what is better from a certain point of view is to think about the opposite of the non-convex. Okay, so I will try to describe very shortly what is the property for an order for being non-convergent. Okay? And you will see this is very, very, very transparent. Okay, so so remember that. Let me remember the definition of the property. So an order is Conrad if these three conditions that I will write are equivalent. The first was that for every F, there exists this complex jump. And well, I will just write in a short way. So there is this complex geometry, and this is Archimedean, and this embeds into R because of Holder's theorem. So Adam gave the full definition of this because it's very long. The second thing is that for every positive element, and for every for every pair of positive elements, there exists an n such that fg to the power n is larger than g. And the third thing I showed yesterday is that this exists for every f and g. Then for every f and g, actually fg to the square is larger than g. Okay. Okay. And I gave a direct argument for proving this without passing through the Conrad's theory, which was somehow very tricky. So this was the argument of Jimenez. Like very much, and I will try to explain this argument now in a dynamical. So what's really happening? So the argument was as follows: if fg to the square is smaller than g, well, if it is equal than g, then f should be the inverse of g, but f and g are positive, so that cannot be the case. Then f times fg to the n is smaller than fg for every n. That was what we proved yesterday. So I call this h. So the proof was like this. Okay. Now I will try to explain what's really happening. So with a graph, with the dynamical condensation. So you will see what's happening. So remember that there was this function phi from gamma into R, and I impose the condition that phi to the identity is equal to 0, and phi h of phi of some element equals to phi of. Okay, this is the actual. Okay, so in that case, this means that I will use another color. So this means that f applied to the point associated to g to the square is smaller than the point associated to g. Okay, so I will just denote, instead of denoting phi of this group elements, I will just denote the elements. Okay, so somehow 0 is phi of the identity. So I will put in my graph just the identity. This is the identity. And the image of f by f of the identity is something. This is the graph of f. We know that it is above the identity because f is positive. And now the condition is that f moves the point corresponding to the square to something below to g. So you will see that one picture that arises. So let me say this is g. This is the graph of g. So this point is g because this is the image by g of the identity. And then you go to this point and to this point, and then you go there. This point is g to the square. Can you follow this is just composition of maps. And the condition is that f moves this point, which corresponds to this one, of g to the square is smaller than g. So it's something like, no, this is not okay. Sorry. This is now this is g, and now this is g to the square. That's okay. Okay, so this is the level of g, and f and this point into something below g, or something here. And then you see, the graph of f has to close the diagonal. This is the first thing. This is the first thing. And now you look at this element h. H was f times g. So what is fg? Oh, there is another, the green one for h. So this is g, and this is g, and this is the image of g by f. this is FG, and the point here, and now you have H. And now you look at this. So H of G equals to FG to the square, which is smaller by hypothesis than G. Okay, so H of at this point, so H is a graph that starts here, and H at this point is smaller than G, something like here. And then here there is a very strong crossing of the diagonal. And now what happens is something very well known in dynamics. So there is a fixed point here, and when you iterate by H, when you perform all the iterates of H, well, you get this point, then you go here, then you go here, and you keep trapped here, and you will never cross this level. Okay, and this is the reason why you have this. Okay? This is something that you can see now. So in my group yesterday it was just some easy computation, but this is something you can see. And the point here is that the Conrad property, the failure of the Conrad property, is a property that involves a very rich dynamics. There is many graphs that are crossing the diagonal and that they are mixturing. And actually, there is a very nice characterization of the failure of the Conrad. So I will write it here. This is a proposition, and actually this is very elementary to establish. I mean, it doesn't require any and this is really taking the inequalities and producing elements. So the proposition is that an order, a left order, is non-Conrad, but only if there exist four elements, H1, H2, F, and G, such that H1 is smaller than F of H1, is smaller than G of H1, smaller than F of H2, is smaller than G of H2, is smaller than H2. This is an equivalent way to see the failure of the Conrad. I like to draw this way. So you have H1 here, H2 here. The element F moves these 2 points into some interval here. And the element G does the same but to the right. Okay. So this point is FH1, FH2, GH1, GH2. Okay. And now if you look at the graphic, the element, you will see this behavior, and there are many elements crossing the diagonal. Okay. Now, some consequences of this way of thinking. So the first thing is that well, we already proved this, but again, the space is closed. Why is that? Because the complementary is open. Why is that? Because the complementary is the set of orders for which this kind of thing exists. But if you have an order with for which there are elements like this, and you have an order which is very close, you have the very same inequality. And since this is a characterization of being non-Conradian, the new order is non-Conradian as well. Yeah?
Is the GH1 be greater?
Sorry. Yes. Yeah. Okay, thank you. Yeah. This is the picture. Yeah. So there is a contraction. There is contraction somewhere. Yes. And this is very natural to expect, because in the case of the Conradian order, there were these Archimedean quotients. So the actions, you think, I like translations. And here, when you are non-Conradian, there are contractions somewhere. Okay.
FH1, FH2, right? Not
okay. Right. Okay, so the proof, why is that? So the complement of this, and actually this is something that I tried to do. I didn't manage to do it, but if you impose some inequality, some condition like this, you will immediately and you look at the orders for which such a family of inequalities are satisfied, you will get a family of orders, which is an open set in the space of left orders. Okay? And I don't know whether there is something in between left order and contrarian, which is weaker than contrarian, but which is still interesting. Okay? And which can be described in algebraic terms. For instance, no, I like to call this a recipient pair. So this is a terminology that comes from information theory. This is classical information theory. But actually, you can look at the orders that they may produce resilient pairs. So, what about orders? What about the set of orders that do not produce? But I will take the one that do produce double resilient pairs, which means that there is contraction on some interval, and immediately to the right, one of the elements keeps contracting and the other expands. Okay, it's an expansion. So this can be encoded by finitely many inequalities, and this gives you a set of orders in the space of left orders. And it is open because it is characterized by finitely many inequalities, and well, it is possible to describe these orders in algebraic terms. Okay, so it's possible to describe the complementarity of this set of orders.
All right, can you just explain again, what do you mean by the double? You have just this picture.
I can give, I wrote the inequalities here, so, okay. I think that's a double pair is, in my mind, something like, have some element F, and then it becomes like this, and G crosses the diagonal. And the point is that F and G contract on this interval, and here G is also contracting, but if you take the inverse of F, it also contracts. Okay? So in terms of inequalities, it's like H1 is smaller than F of H1 is smaller than 2, smaller than G of H1, smaller than G of H2, this is smaller than another H bar, which is smaller than H2, which is smaller than G of H2, which is smaller than G of H2 bar, it's smaller than F inverse of H2 bar, which is smaller than H2, sorry. F inverse of H2 bar is smaller than H2 bar. This is a way to encode that this happens. Okay, but the point is the following. Now consider the set of orders for which these elements do not exist. The closest subset of the space of left order. Is it possible to characterize them in by a sentence like this? Is it useful for something? I don't know. But I was thinking about, so let me give another application of this stuff. Oh, I don't want to. So non-contrarian means that there exists H1, H2, F, and G such that this happens. Okay. So Adam mentioned a theorem of, and he gave a proof, a very nice theorem by Rolsen. So it was if gamma has no pre-subsemigroup, then every order on gamma is contrarian. Well, and the proof using this is more or less direct proof. If there exists a contrarian order, a non-contrarian order, you have this picture for the realization of this non-contrarian order. And when you have this picture, you have the ping pong game. Well, this is what is called the ping game. You don't use you only go to the and the point is when you have this picture, immediately you know that the semi-group generated by F and G. And well, I was thinking about this kind of thing because of the question of period union, whether if you have an orderable group without a free subgroup, whether you can get a Conrad order. In that case, I needed to pass to the inverses and so on. So now I have we'll finish with one of my favorite theorems in this framework, which is a very nice theorem by Dave Morris. And which says the following. So remember that there was this theorem by Conrad and Brodsky that said that a group is Conrad orderable if and only if locally indicable. So Alan in his minicourse gave the proof of this direction using Conrad theory, and the opposite direction not using the Brodsky approach because it's very hard, using a kind of Bern-Scale type argument, which is kind of compactness argument. Okay, and the theorem of Morris is that, well, there are many groups. There are many groups for which there is no Conrad order at all because they are not locally indicable, they are not orderable groups which are perfect and so on. But it cannot be the case for an environment. So the theorem of Morris is that if gamma is, so I will restrict to finely generated, or otherwise I have to go into discussion of anonymity. I don't want to do that. So if gamma is finely generated, amenable, and left orderable, then it is Conrad orderable. And because of Conrad's theory, it is the real conclusion is that it is locally independent. For instance, an amenable group that left orderable cannot be perfect. Okay. Yes. Okay. So this is the statement of the theorem, but actually this is what we do actually, following the argument of Morris. The argument is really fantastic. So I will give the argument to finish place. So I still have here. It's okay, 20 minutes. And there are two things you can do when you have an orderable group. You can look at a specific order and look at the dynamical realizations and look at the dynamics and the action, but look at the relations and so on, or look at the action on the space of left. And what it does is to look at the action of gamma on the space of left order. And because gamma, I assume it is finitely generated, this implies that LO of gamma is a compact metric space. And now, so what I want to show is that there is a Conrad order here. I just need to detect a single order. But the point is that since gamma is amenable, one of the many definitions of amenability is that for every action on a compact metric space, there is an invariant probability measure. Okay? There exists probability measure, the mu invariant under the action. And the claim is really fantastic. So for this invariant probability measure, the measure of the subset Conradian left orders, in particular, there is a Conradian. Generically, for this measure, an order is Conradian. But again, you don't put the hands on the order. You only know that this has to exist. Okay? This is the dynamical part of the group. So you can really detect the order. You only know that there is at least one. So understanding what it is depends on the group actually. Because, so let me give an example. So for instance, this is a very nice example to understand a little bit what's happening. So if you take the boundary axolital group, in this group, there are two kinds of actions and there are two kinds of orders. There are the affine actions and the actions that come from the by orders. Okay, there are 4 by orders And they are left orders that lead to affine actions. Not necessarily the obvious one, because you can change B, if B is the translation by one, you can change it by the translation by minus one and so on, but it doesn't matter. So this lead to affine actions. And because the actions are affine, you have this contraction property. And because of this characterization, this corresponds to non-convariant orders. So in the space of left orders of the bounded solitary group, which is amenable because it is solvable, there are only 4 points which are convariant. Actually, they are by invariant. So when you look at these dynamics here, the dynamics of the action of the bounded solitary group into the space of its left orders, the dynamics is somehow contracting towards this value. Okay? Because these are the supports of the invariant probability measure.
Every left order here is giving you an affine action.
No, every left order which is not one of the 4 by orders gives you an affine action. Yes, something which is somehow conjugate to an affine action. So, and the dynamics here is something like this. I don't know how to draw this picture, but this is the only possible support for invariant probability measure like this. And actually, if you take the direct mass on this point, since this is a bi-invariant order, it's a fixed point for the action. So this is the support of an invariant action. It's just okay. Let me go into the proposal, because this is really fantastic. Take an element which is not the identity, and denote over of F the set of orders for which this element is positive. So for an order, this element can be positive or negative. We only keep this subset. Now take any G in the group and denote P of FG, the difference between O of F minus the preimage under G. And now denote by B of F the union along G of BF of G. And now denote by B the union of B of F different from the identity. So here B is for bad. Okay, this is a bad order. And the reason is that there are 2 claims. The first one is that if an order is in the complement of the bad orders, then it is convariant. The good news is that the measure of B is here. Okay, let me go into the first part. Why this convariant? Because we did everything to get a convariant. So I have an order here. Let F positive, and actually G, I don't need to impose the condition. It's positive, but I will impose it. So and G positive for this. Now, since F is positive, this means that the order, let me denote it by a star. So this is the particular order in the complement of the set of particles. Since F is positive for this order, this means that this order belongs to this set. Okay, because this is the set of orders for which F is positive. But this order doesn't belong to B. So in particular, so it doesn't belong to B, it doesn't belong to BF, so it doesn't belong to BF of G for every G. So it doesn't belong to this set, which means that it must belong to some of this set. Okay? So the order is in the complement of B, implies that the order is in E of minus n of 2F for some n. Now, what does it mean? It means that the order is in the pre-image of O of F. No, sorry, I made a mistake here. I need, doesn't matter, but I think I need G to the N. I need plus N. It doesn't matter at all. Okay, we will see. It doesn't matter. Okay, so this belongs to this, so G to the minus N. We will see. So the order to which I apply G minus N belongs to O of F, which means that this is an order for which F is positive. Okay, so F is positive for this order to which I apply G to the minus N. And by definition, this means that the conjugate of F by this element is larger than the identity by definition of the action. And this means that Fg to the n is larger than G to the n, which is actually stronger than the contrast property because we just need to be larger than G. But since G is positive, G to the n is larger or equal than G. Okay? What the order is. Okay, so this is a very, so Alan mentioned this property. This is what calls recurrent orders. It's a stronger property, but I think that the set of recurrent orders is not too close inside the space of orders. So, okay, so let's justify the notation. So this is B. And now the proof of this if that mu of B equals to 0. Why mu of B equal to? Well, B is the union of countably many sets, each of which is a union of countably many sets. So actually what I have to prove is that the measure of this for every F and G, etc. Okay? For every F different from the identity, for every G, the measure of O of F minus union of the image of these sets. So this is so I like to write this way. So these are really the pre-image of the set by A. So I have to prove that this vanishes. And so far I didn't use the measures. The point is that this is an invariant probability measure. Okay, mu is invariant probability measure. And for people coming from dynamics, this is obvious. It's a magic name here. The father of dynamics. Poincaré. This is Poincaré. Poincaré's recurrence theory. And why is that? So Poincaré says that if you have a system, a dynamical system with an invariant probability measure, so almost all the orbits have to come back close to itself infinitely many times. And here what we have is a set. It doesn't come back to itself. Well, it has to be of simulation. And the proof of this works like this works. You can check it. But this is proof is of this part is so the sets G of I of this set are 2 by 2 division. So you have the set, this set, and then you have the image by G of this set, and you have the image, and so on. This is by definition. They are 2 by 2 division because if you get some intersection, then you can check. This is classical. But now the point is that the measure is invariant. So if there is some positive probability measure here, the measure here is the same, the measure here is the same, and so on. So you get infinite measure. But the measure which is invariant is the probability measure. So this is impossible. So the measure has finished. Okay, this is not the strongest form of the Poincaré recurrent. This is actually the simplest case of Poincaré recurrence, but this suffices to establish the field. This is really a great. So I will stop here.
Thank you.
Setup.
Go ahead.
Thank you.
Okay. Yes,
Like, do you have the same setup? Can you say anything about the measure of the by orders?
set of by orders. The problem is that again, the by orders are the fixed point for the conjugacy. You have a fixed point, then you have the direct mass on this point, which is in the value. So maybe you should look at the action of the group of automorphism of the group on the space of I. But in that case, in general, group of automorphisms are not amenable. It may be very, very large.
So this is proving it for like any invariant measure? It's one of the.
Yeah, that is interesting. For any invariant probability measure, you have this. But actually, in the case of the bounded solitaire, there are 4 invariant probability measures. Java. Concentrate on the by order.